I'll decide tonight. All right, let's get started. So we were arriving almost to the sign negation, right? So one of the features in doing a complement in a base 2 binary is the feature that whenever you add a value such as x with its negated value, for which all the ones were switched back to 0 and vice versa. So all the zeros were switched back to 1. So when you add these two, always in binary word you're going to see -1, right? So technically, if you want to make that equal to 0, so you need to add a +1 there, so that when you complement 1 as a sign negation, so x plus x bar plus 1 is going to be 0. Okay? You're going to use this property in your lab questions or exercises as well. Perhaps you've already seen it. Just wanted to make sure that I've passed through this. So now we start by representing instructions here. By now we got familiarized with some of the arithmetic memory operations, and we sort of have a high level and general idea how we're going to compute certain stuff, right? So now if we zoom back one level, how are we going to represent instructions? So an instruction could be a load instructions, it could be a save instructions, it could be a store instruction, it could be a division instruction, and so on and so forth, right? If you want to represent them in a binary format that a hardware beneath understands that, how are we going to represent that, right? In RISC-V, as we talked about, we have a 32-bit instruction board that all those RISC-V instructions are encoded. Some of it has a very nice property because it gives you a regularity, so it's pretty small. The format is known, so you can almost decode it by just looking at it, right? When you get used to working with these instructions, you kind of know them by looking at them. All right, so let's see, first of all, what a hexadecimal is. As you might know previously, so instead of base 10 or base 2 for a binary, so hexadecimal is base 16, right? So your numbers starts from 0, but instead of stopping at 9, so you can go on up to 15. So after 9, in order to call 10, we call it A, 11 we call it B, and C, D, E up to F, which is 15. So if you represent that in a binary, since hexadecimal is on a base of 16, which is 2 to the raise of 4, so by 4 digit you can represent 1 hex, right? So 0 represents 4 zeros, and up to the other extreme, which is F, and 4 ones. So in this case, if you want to represent this value, which is E, and you can simply see that E was 14. C here, you can have a look at it, and then this was 10, 11, and C was 12, and so on and so forth. You can represent all of those with each tuple of 4, and that's how you're going to convert a base 16, which is a hex, to a binary. Is that clear? Okay. And the other convention that we use for hex, if we didn't mention that this is a base of 16, whenever you see something like this before a number, that shows that it's going to be hex. So 0x, and then the rest. All right. So now let's have a look at the RISC-V format instructions. In general, we have 3 different format instructions for RISC-V. So we call them, we distinguish them with R and I and S, which we learn later on, right? So let's start with the R format. So as we knew, we have 32 bits available here, right? So if you add these 7 bits, 7 plus 5 is 12, and then 17, 20, 25, and 32, right? So we have this space at our hand, and we want to make sure we take the best use of it. In the case of R format, we have divide them into these 6 categories. So the first one, which is func7, is a 7-bit function code, right? We're going to use it for our function codes. Again, refer it to your green card, which we will provide it to you in your lab as well as one of the attachments inside your local folder. And all of those are listed there, so you can use it at any time you want it. All right. The next 5 bits is for the register source 2, RS2. The third one is register source 1, so both of them are 5 bits. So you need to input 5 bits for the source and destination. And as you know, how many distinct value I can present by 5 bits? So I have 5 bits. So how many distinct values in decimal I can present? Remember you had 4 bits for hex. How many distinct values you could present with 4? 16, right? So how many distinct values of decimal you can present with 5 digits?
32.
Yeah, why? Yeah, because each of those digits can take either 0 or 1, right? So you have five locations right here. So you have 5 locations, either 0 or 1. 0 or 1, 0 or 1, 0 or 1, and 0 or 1. So each of them gives you 2 options. 2 multiply 2 multiply 2 multiply 2 multiply 2 is going to be 32. And you see that in RISC-V, you have 32 different registers, right? So everything makes sense. They have to be the same size. So your RS2 and RS1 are 5 bits because you need to present them with different register numbers. And let me just go back to show you some of those that you already know. Here, starting from x0, which was a constant value, up to x32, we have different things. We're going to use them for different reasons, right? All right. So we have 2 registers, source 1 and source 2. We have another 3 bits. We assign it for another sort of function type code, which we call it additional code. It is again in your green sheet card. So and the 5th one is the RD, which is the destination register, another 5 bits. And at the end you have the opcode, which represent actually the operation code of your instruction. And we're going to use that with 7 bits, right? So let's see an example here. So here, we wanted to present an add instruction, right? X9, X20, and X21, right? So by just looking at the assembly, which is the add, so you're going to understand that this X20 and X21 are the source, right? The first source and the second source. So you can just fill that up easily. You can just put it on this line. We're going to put this decimal format, which is to the base of 10. This is base 10, and this is base 2 at the end, right? So your base 10, and so you're going to have RS1 and RS2 as your 20 and 21. Your func 3 bits is 0. Your destination was X9, which is 9, and the opcode assigned with add is 51. How can you know that? You're going to refer to your green card again, right? And then when you convert it back to binary, so for 21 you're going to have 10101, so for 20 you're going to have 10100 and the rest, okay? And then when you concat all of this together, you're going to see this binary instruction of 2, or each of those 4 can be converted back to hex. So this is the hex. So this would become this, and the last one become this. Right? This is in hex, 16-bit. Is that clear? Yeah, question.
Which one
for the opcode is 51. Is that for add?
Yeah.
Yeah. What's a function 3 and function 7?
So based on each of the instructions is different, but you can refer it to your green sheet as well. It's there.
Does it change by like the operation? Like if it's back to
Sometimes yes, but sometimes no. Yeah.
What does RD mean?
Registered destination. Yeah, and RS are the source 1 and 2. All good? Okay. All right. So what we have basically said is you have X9 as your destination, you have X20 as your RS1, you have you have 21 as your 2, and then you would convert it back to hex or binary, right? Okay, so there are 2 other format instructions. So we already saw one, which was the R format, right? So we have another one called I format. Yep.
So in the previous slide, how did you get opcode as 51?
It's intern green card. Yeah, you can refer to that. Its operation has as an opcode. Yeah. Okay. All right. So mostly for the I format, we're going to use it for immediate arithmetic and load instructions. So for load, because we needed more instructions for our immediate, so 7 wouldn't be enough. Now we need to use 12-bit for that. So we got rid of the func 7 there, and that turned into a 5-section instruction. So in this case, now we have 12-bit for immediate. For register source 1, we have 5 bits. We have the same func 3 bits, and then the destination, which was the 5 bits. Your opcode will be there again. All right. So the only thing that we have to take into account that in order to assign that immediate 12-bit, right, we need to offset. We need to add the offsets to base addresses. And then in this case, the tooth complement or sign extended are supported as well. So another design principle of RISC-V is good design sometimes demands some compromises, right? Sometimes we cannot address all the different difficulties that we are dealing with just a single sort of design. That's why we need to come with 3 different format instructions. Okay?
So I have a question. What if we add a number that is more than 12 bits? What would happen?
So
the constant would be more than 12 bits.
Right.
What would happen?
So in this case, for the load operation, we need to use this. You need to offset it by the base address, or we're going to use a tooth complement. I'll have an example for you. No worries. Okay. So let's see the third one. Well, actually, we have an example right here. So before going to the RV one, okay. So now we want to load the 64th address in memory of the register X3. Assume it as an array, for instance, and then we're gonna load it to this register X9, right? So for this, again, we're gonna do the same thing. Your register source of 1 is gonna be 3, right? Your func is still that 3-bit it has been predefined for load. Your destination would be 9 here. Your opcode for load would be 3 here. Okay? Again, just like the previous one, you have to convert this from hex to base 2, and that's the final example. This is the hex one. So this is the 2. This is the hex. Yeah.
Why does it say 4?
Can anyone know the answer?
Is that the value you're trying to get out of X3? Is that the value that you're trying to load?
The 40?
Yeah, I think. Because it says.
Does anyone know the answer?
It's like the string like 0x0, like the last three will be 040, hold that number, right?
Here's the X. That's the X representation. Here's the X representation of 64.
Was that clear?
So when you're saying that you're adding 64 to the base register, the offset,
Okay.
what are you adding? Like bits you're adding?
Could you be louder?
When you're saying that you add a 64 offset to the base register X3, what do you mean by the offset?
So when we are trying to find out a specific value inside X3, so assume it as an array like A. So we are trying to access the 8th number of that array, right? A of 8. So we start from the base. The base could be starting from 0 or from an offset inside an execution of the code, right? So you need to have another pointer for that. But for now, just assume it, you started from 0, from base. So by going up to 64, we pass 8 bytes, right? So that 8th element of that X3, right? And that's why that 64 refers. Questions?
40 is caps.
All good? All right, let's have a look at the third one, which is the S format instructions. So now again, we have 6 different classes or categories here. So what we did here is, because the S format, we're going to use those RS1 and RS2 together, we wanted to make sure these two are together. So we had to sort of cut the immediate into 2 halves, not even halves. So from the first 5 bit are in the penultimate one, and then from 5th to 11 is the first one. So these two are actually going to get together. These are together. But we wanted to make sure these two are together. That's why we present it this way, right? So the RS1 is the base address register number. The RS2 is the source operand register number. And the immediate one is the offset added to the base address. Okay, so let's see an example of this. So we are storing X10 and 80 of the register X2, right? So 80 I've put here the hex of 80, which is 50, and this is the binary of that hex. So in that case, these two together are actually representing the value here, right? 0 to 4 is here, 0 to 4, the first 5 are here, 1, 4, 0, and then from 5th to 11 is the rest of that, hex 50, okay? And these two are 10 and 2, which are the RS1 and RS2 of my operation. Is that clear? And the opcode of ST was 51 again. I've uploaded the green card sheet on your Moodle, so you had already that. I'll make sure I have it available in your lab as well. Yeah.
Sorry, could you explain what the 80 and the bracket X2 stand for again?
It's just the same as your friend's question. So we are trying to offset the memory by that amount, and since that each of those represent 8 because they are 1 byte, so that 80 is actually 10. So like you're storing to the 10th element of that X2, right? Okay. So now you can see this, which we already saw that. In one shot, now you can see all of those instructions. So for some instructions like add and sub, we are using the R format, right? You have the func, you have the RS1 and RS2, func3, destination and opcode. So that was your first. And then you have another type, which is the I. We're going to use it for add I and load. And a third one, which is the format S, we're going to use it as a store here. And by a store, when I don't add anything to that, is store double word, which is all our 64-bit. Okay? All right. Now, let's see how a computer stores program, right? So we kind of understood what's happening inside the processor when it's going to access different things from memory. Let's talk about how we're going to store things in memory. So your memory normally has a huge, a much larger space than your processor's registers, although they are smaller, right? So you can see as an example, when your computer is running, so perhaps your memory is taken up by, your editor program. Perhaps you're running, I don't know, your Word or LaTeX or something else. And then you have other things going on. Your machine code is running as well. Your compiler has already compiled and run that. And another program like a recounting is running. So these are the different things that takes up your memory, right? So whatever actually runs on computer need to be stored in memory, and by the time you switch it off or when you reboot that, because it's a non-volatile memory, it's going to be gone. So let's see what are other instructions that we can apply as logical instructions. Okay, let's go back to our instructions. So now we need to define other type of operations here. In Java also, just like as C, so we have the shift left here. In RISC-V we call that shift left logical immediate, so SLLI. So for shift right we represent it in C by this. Java has a little bit different notion. In RISC-V we're going to show it with SRLI. And these are the other logical operands, so you can do the bit by bit and this is the ampersand. So either you're going to do the and or and I, and then bit by bit or, and XOR, and not, right? So these kind of operations are very useful in order to extract certain things from a group of bits in a word. You can do many things with that actually. You can build a neural network with that. So anything is possible when you add logical and an or XOR. Actually, with the XOR itself, you can build a computer. You can build a CPU actually. Okay. So let's see an example of shift operation. So by shifting, basically we are trying to imitate multiplication and division, right? Shifting right and left. And in binary, which you are only dealing with 0 and 1, by shifting left and right, you are actually doing a multiplication or a division. So let's go back to the presentation of our instruction. So we have, in this case for shift, we have func6, which takes 6 bits. The immediate takes 6 bits. The RS1, the first source, takes 5 bits. And then the destination takes 5 bits as well. So you have the opcode of the 7-bit for that, right? So in this 6-bit, we're gonna actually show how many positions to shift, right? So either by shifting left and right depending on the opcode. So, for instance, the shift left logical is going to shift left and then fill the rest with 0. Right? On the other side, your shift right logical is going to shift right and then fill the rest with 0. You have two more SLLI and SRLI, and that they're going to do the division. So for instance, in this case, they're going to divide it by 2 to the raise of I. It's going to be unsigned, and the other one is like, it's going to multiply it by 2 to the raise of I. So these are pretty easy. I mean, I don't want to just to memorize it. You can just play around with it in the lab later today and see the output. For instance, yeah, for instance, that's an example for shift left of the word. Let's see an example of AND. So you want to AND these two, so it's going to find those and it's going to select some bits, clear, others is going to be 0 because 0 and to 0 is going to be 0 again. So those that are not 0 are going to get, are interested for our AND operation to be working on, right? So the output of this is going to be 0 and 1 and it's going to be 0. 0 and 1 would be 0 again. Only on the case of both 1s, because it's an AND, it's going to output 1, right? All right. For OR, just like the AND one, you're gonna just do an OR logical operation. So either of them, if either of them were 1, you're gonna have the output as 1. For XOR, right? You're gonna do, if either of those were 1 only, the output would be 1. So is it clear up to now?
How are the bits selected for those operations?
So you can do the AND for both registers, and so if both of them are 0, definitely the ANDs would be 0. So there's no reason to apply that, right? I mean, if you even apply that, it's going to be 0 again, right? But those that are non-0 are going to get selected.
What if we have 10 represented 4 bits? And we use SLI, what happens then? Because we're running out of space, right? And what happens? What does the program respond? How does it respond?
So,
we have 10.
So you're shifting it to right or left? Okay, and then?
We have 10, so it's 1 0 1 0, right?
Right.
And then we shift it left, and what happens? Where does the one on the left go? Because we're running out of space.
So those on the left were already 0, right?
Those on the left? It's 1 0 1 0, right?
Right, and the rest of the 6, I mean, if you are using for double word, so the rest of those 64 bits were already 0, so you weren't using them. So you just shift those 3 or 4 digits one to the left, so the one on the right is going to be 0, and then the rest are 0 again, right? If you overflow all of that, that shows that, I mean, if all of them are 1 in unsigned, that was your upper bound to use as your double word. You have to present it in a different way. Yeah.
How would you divide by a number like, say, 13? It's not like an exact power of 2.
Right. That's a good question. Does anyone know the answer?
Can't you just do 2 to the whatever value is closest, and then just keep adding or subtracting 2 to the 0?
This is one way, yeah. We'll say more about that, but this is one way. You have to sort of come up with, again, there is no single best answer. Sometimes you have different answers because it's logical operations. You can just go one above and then go back your way down, or just start from one below. There are different ways. In some methods, and some of the methods are having less instruction, fewer instruction count. Some of them are faster, some of them are slower. So these are the caveats that you have to deal with here. Okay, so now let's talk about the conditional operations. So now that we know how we're going to do arithmetic, the logical operations, now we need to see how we're going to imitate the loop conditions, right? The while loop, the for loops. How we're going to go back to the same place and keep repeating. How we're going to jump. And let's see how we're going to do that. So we have two important instructions here. So BEQ and BNE. So branch if equal and branch if not equal, right? So that basically says that if these two are equal, so RS1 and RS2 are equal, which is this condition, then branch to the instruction labeled as L1. So perhaps somewhere in your code before you have started that, so you have annotated that with L1, and then at the end of that, perhaps your for loop, you want to jump back to that L, given the condition has met. Okay. On the other side, you can have another way to define that. You're going to branch if not equal. So if these two were not equal, you're going to branch to that label L1. Okay. So with these two, we can define a variety of while for loops. So here, let's see an example. So we have a C code here. So that says that if I was equal to J, and this is the logical operation, F would be assigned as G plus H, right? Else, on the other case, on the else condition, you're going to have to assign F with G minus H. So if you draw that sort of control flow, so you're arriving here. You're arriving here. So you're running your code. There are so many things, and you arrive here. So now you have to have a conditional operation here that checks if I is equal to J, whether or not. If yes, you have to follow this path. If not, you have to follow this path. And this will give you, and B and E, right? This will give you this. So if you compile that, you're going to have a branch not equal of x22 and 23. So 22 and 23 are going to represent your I and J. If they were not equal, they're going to go to the else case, which is this. So that's your else case. And if they were equal, they don't have to jump anywhere, so just they carry on executing the code, right? So it's going to go down, and then that's your for case or while case. We can just say the true condition was met. Yeah.
What if you don't have the BEQ line and you don't have the exit path? What will happen?
So that means that, I mean, you have defined an instruction with only two registers?
Well, so after the add instruction, if you don't have the branch of equal instruction,
I see.
what's going to happen?
You're not going to come back to the same place that you check for I and J. You just carry on executing the rest. So you have missed one of your branches. It's as if you didn't have a loop. Or just you loop once and then you left the loop. It's incomplete, right?
So wouldn't that be the same thing as having that branch?
For one iteration, yes, but after that, no. So here, you arrive here, so you were running your code, you arrive here, right? You need to check if you're going to follow the loop or the else. So this is either the for or the while, or you're going to do the else case. In a case that they were not equal, you're going to follow the else case, right? Here. And then here you have to check that are you going to exit, which is this, or are you going to go back to else here?
So let's say that they are not equal, which brings the
Which of them? X22 or
X22 and X23 are not equal, so you run the else path.
okay, and so you arrive to the add, and then so you add this.
X20 from X21 and assign to X19, and then which instruction will be run after the else path has been run? So after the subtraction instruction, which instruction will be run?
So if you reach the subtraction here, you're gonna exit after that because you're already here,
Okay.
right? You're gonna exit the loop.
So it will not return. It will
Yeah,
not go back.
yeah. If you met, yeah. But if not, you're gonna just go back to this loop. It depends actually how did you define the loop, right? In this specific case, we're gonna go either this way or we're gonna go that way, right? Is that clear? Yep.
In the BEQ, why do you compare x0 and x0? That is same one.
Does anyone know the answer? That's a good question.
Does one just break out no matter what then? Like it's just gonna exit because it's true always.
Yeah. So when we want to break no matter what, we call it unconditional, right? So without any condition, we want it to break. The others are conditional branches. If the condition was met, we're gonna do that, right? Sometimes it's just your jump, right? Or go in high-level language. Sometimes we have go to, right? Go to, and many times you've been advised not to just use go to. It might just break your code if you don't use it, appropriately.
So like it could be anything like x1 and x1, x2.
Yeah, because all the time x0 is equal to x0, right? So you're gonna exit.
So like
It's like go to, like whenever you reach this, go to the other line or go to the place that I need you to go to, right?
So in this piece of instruction, in this piece of code, where there's no instruction to how to compile to go back.
Yeah. Yeah. I mean, this is just one iteration of a sample loop. Yeah, we could have defined something else that unconditional, or there was another condition that comes back to the previous one. Yeah. Just to simplify, I provided like this. Guys, is it clear? How do we branch these two lines? Okay. So, let's see a more complex one, a while one. So while save I is equal to k, I plus 1. And I is in x22, k is in x24. And the address of save is in x25, right? So now, we are trying to implement a loop here in RISC-V code. So, first of all, we do SLLI of x10 and x22, which represents our I multiply 8, right? Suppose there was a C function, there was a C program doing that. And then we're going to add x10 and x10 of x25, which is actually save I equal to x10. Then we're going to load the base, the very first time, the base address of that, which is the save I itself, and I was 0, the first I, to register x9. Then we're going to go to branch not equal. So we have to check for x9 and x22 if they were not equal. Right? They're going to go to exit. Where is exit? It's after the second branch. So either we go this way, either we come back and we go here, so 1, or we come back here and we carry on. 2 different paths. Then at the end, we're going to check for another branch, which is unconditional here. Right? No matter what, because these two are always equal, we're going to branch if they were equal. And we're going to go back to loop. So that means that in one case, you're going to have a loop. In another case, you're going to exit the loop, right? You saw how did we implement this? I'll let you have a look at this for a while.
Why are we multiplying it by 8 in the first line?
That was just some preliminary, computations.
And why are we saving it in 2 different registers? We already have it in X10, right?
I mean, that's just an example, So now you understand when you define, when you write a high-level language like Java or C#, C++, by each of your conditions in your loop, you might end up with so many different instructions in the lower end, in your assembly and then in your hex, right? So the way you define the way you write your program, depending on the compiler you use, you're going to have different output. And now you understand how perfect you need to write those codes so that the assembly generated out of your codes could be perfect as well.
Shifting the first line where we shift, is that just like arbitrary?
Yeah, it's just some operations to see, yeah. It's just some multiplication. Questions? Okay. All right, so now, by seeing these 2 small examples, you're going to see that when you come down into a program, in some part of the program, you have some branches, you have some loops, and then you exit out of that, right? So how can we distinguish between this and a simple, straightforward execution of a program? And that's how we define it. We define it by basic blocks. So a basic block is a sequence of instructions with no embedded branches. So when we talk about basic block, it's like you don't have any branches, you don't have any branch targets. So you just follow through the instructions, right? No jumping, nothing. So suppose this is your execution flow. So this portion before branching somewhere else can be called a basic block. This is one of the basic tasks that a compiler can identify by parsing your code. And also hardware, some advanced hardwares can accelerate processors, can accelerate the execution of a basic block using different hardware technique. Some of them you might get to know in an advanced computer architecture course or perhaps in other courses. But definitely in grad level there are courses that deals with how the hardware can accelerate the execution of a basic blocks and non-basic blocks actually. All right, so let's talk about some more conditional operations that sometimes you might use. So it's BLT, which is branch if less than, and then you have branch greater or equal. So these are 2 different things that you can use. So if if RS2 was greater than RS1, or from the other side, RS1 was less than RS2, you're going to branch to instruction annotated by, labeled by L1. And then on the other side, if RS2 was greater than or equal to RS2, you're going to branch to label L1, right? And here's an example for that. So we can use the BLT and BGE also for comparisons, both in signed mode and in unsigned mode, right? For unsigned mode, we have an extension of that which is called BLTU or BGEU, which is both of them are for unsigned. And for the signed, these two that you already saw, they are doing the sign comparison. For instance, if for the first one, X22 and X23, we can do a sign comparison with BLT, and that would be the results. But for an unsigned comparison, they need to compute the actual value that these ones are representing, and then they're going to come up with the comparison. So this represents a way larger value than that with just one, right? All 0 and 1. Okay? Clear?
Is there a BGT and BLE? Like, is there just greater than and less than equal to?
So instead of smaller than equal?
Yeah, instead of BLT, is there a BGT as well?
Oh. I mean, you can build, you can use these to build your own. I don't think there is out of the box. Yeah. Using all these logical and conditional conditional operations, you can devise and stack them up to represent many other things. Actually, everything that is running on a computer, right? Questions? No.
Sorry, for the first example, how do we know the first one is -1?
Because it's a sign. So in the sign format, you have that first, which is the most significant bit, either 0 or 1, and that represents your sign. If it's minus or if it's plus, right? Got it? Yeah. For the unsigned version, we just treat it as another most significant bit of the value. Okay. So using this, we also can check the bound check, right? When you are doing for loops, for instance. So we can check index out of bounds for array by treating signed numbers as unsigned. So for instance, if you want to check for x that whether or not it is between n and greater or equal than 0, we just have to use branch greater than or equal unsigned. And then if that was the case, you're going to just output, for instance, to go to an index out of bound as a label address, just to represent an error, right? And by definition, we call this minus VE and plus VE for positive and negative. So they're just sort of an abbreviation of negative and abbreviation of positive, right? Okay. Questions? Alright guys, so since this is your first lab, I'm gonna just give you 10-20 minutes to relax before starting your lab. And so see you 5 minutes to 7 at lab, okay?